Morning everyone, myself Sneha Jose and today we can look what is rotational spectroscopy. We all know spectroscopy is something that is related with the interaction of matter and the radiation. When the electromagnetic radiation is interacting with the matter, there will be some sort of um, variations or differences that is happening inside the molecule, and that differences will is dependent on the energy of the electromagnetic radiation that we are using. And so today we are looking into rotational spectroscopy, and rotational spectroscopy results from the transitions between the different rotational levels of a molecule. We know in a molecule there are different type of energy levels. They are rotational energy levels, vibrational energy level, electronic energy levels, nuclear energy levels. Among this, from this picture, we can see here, plus, sorry, here we can see in this picture, here we can see the rotational energy levels are between the two vibrational energy levels, and many vibrational levels are inside in an electronic energy levels. So rotational energy level is the smallest gapped energy levels. So we need, for a transition from a lower energy rotational energy levels to a higher rotational energy level, we just need low energy radiation. So we are using microwave radiation. So absorption of radiation in the microwave region is enough for the transitions between the rotational energy levels. So this micro so between the rotational energy spectroscopy is also known as microwave spectroscopy. Okay, and will all molecules show rotational spectrum? No, all molecules will not show rotational spectrum. Molecules should have a permanent dipole moment. Only those molecules which have a permanent dipole moment will be showing the rotational spectrum. So, what is happening if there is a permanent dipole moment? So, if there is a permanent dipole moment in a molecule, that particular molecule can generate an electric field during its interaction with the microwave radiation. So, a molecule with a microwave active microwave, which is microwave, only those molecule which is microwave active will be having a permanent dipole moment, and as a result of this permanent dipole moment, when this molecule, when the rotation of this molecule is interacting with the microwave radiation, that molecule can generate an electric field. So the microwave molecules are generally homonuclear. Microwave active molecules is generally homonuclear reactive molecules such as H2, O2, N2, then molecules such as CO2, CH4, etc. They are microwave inactive, that is, they are not having a permanent dipole moment. But the heteronuclear diatomic molecules such as HCl, H2, HBr, CO, NO, etc. are microwave active molecules. Okay. Then, before coming to the microwave spectroscopy, we should know what is a moment of inertia. Moment of inertia, which is represented as I, is also called as mass moment of inertia or angular mass. It is actually the rotational analog of mass. What is mass in linear motion or translational motion? That is the same thing which is the inertia in the rotational motion. It is a measure of an object's in resistance to changes in its rotational rate. Okay, moment of inertia is the object's resistance to changes in its rotational rate. Actually, this moment of inertia of an object about a given axis describes how difficult it is to change its angular motion about that particular axis. This is here from this picture we can see the correspondence between the linear and angular motion. Here we can see corresponding to the um, um, mass. In linear motion it is represented as m, but in angular motion we can see it is represented as I is equal to m r square, which is I is nothing but the moment of inertia. Okay, here this is the moment of inertia which is represented for a water molecule. Okay. Then the rotating molecules, depending upon the moment of inertia, there are three classes of molecules. There are many. There are actually they are classified into many types, and a body has three principal moments of inertia for the rotational motion, one about each axis. Okay, they are usually represented as IA, IB, and IC. IA is about the bond axis. So IA is the moment of inertia along the bond axis, and IB is the moment of inertia around the plane of the paper, end over end rotation, which arises due to the end over end rotation, and IC is the moment of inertia due to the end over end rotation at right angles to plane of paper. That is, it is represented as IC. So the two perpendicular, mutually perpendicular axis B and C axis are lying in a plane which is perpendicular to IA. So we can see three IA, IB, and IC are actually perpendicular to each other. Okay. Here, molecules are classified into five main groups depending upon the moment of inertia. If IC is equal to IB, that is, if the moment of inertia along the perpendicular mutual axis to the principal moment of axis, that is about the axis about A, the bond axis, if both of them are equal, that is IC is equal to IB and IA is equal to 0, then they are considered as linear molecules. If all the three are equal, all the three are equal, then it is considered as spherical tube. And if the moment of inertia along the bond axis is less than the other two, but other two are equal, then it is considered as prolate symmetric top. And um, if it is just opposite, if IA is less, then it is considered as oblate, and if all the three are different, then it is considered as asymmetric top molecules. We can look into it simple details. What are linear molecules? We all know the molecules in which all the atoms are arranged on a straight line are called linear molecules. Okay, here we can see an example of HCN, which is a linear molecules, and the three axes are shown here. And here we can see IA is equal to 0. That is the moment of inertia along the bond axis. Along the bond axis of the particular molecule is taken as 0, and the other two will be equal. So, as a whole, the molecule will be having only one moment of inertia. Okay, this is the linear molecule. Then spherical top molecules, here all the three will be equal. Usually the octahedral, tetrahedral, icosahedral point groups are considered as spherical top molecules. Here IC is equal to IB is equal to IC. That is, only one uh, moment of inertia is there for the molecule, and all the three are actually equal for the molecule. All the three moment of inertia, that is moment of inertia among for the three principal axis is actually, sorry, three axis is actually equal. Okay, then symmetric top molecules. Symmetric top molecules is divided into two, that is prolate and oblate. If the IA means what? The moment of inertia along the axis, along the molecular axis, is considered to be less than the other two, then it is considered as symmetric top. And if the IA is greater than the other two, then it is known as the oblate symmetric top molecule. Here are the two given examples for this particular molecules. BF3 is an example for obliged. Benzene is an example for obliged symmetric to molecule. And then most of the molecules are asymmetric to molecules, that is IC not equal to IB, not equal to IA. All the three moment of inertia will be different, that is the molecule will be having three different moment of inertia. Okay, now we are going to the rotational spectra for a rigid diatomic molecule. We know it is also known as the rigid rotor model or a rigid rotator model. In this model, this diatomic molecule is considered as two masses with masses m1 and m2 with internuclear distance of capital R, and small r1 is represented as the distance from the center of mass for the m1, and r2 is represented as the center of mass from the distance from the center of mass for the mass m2. So the rotational energy levels is obtained by solving the Schrodinger wave equation, which is given as Ej is equal to h square by 8 pi square I j into j plus 1 joules, where j is rotational quantum number and may have 0, 1, 2 values. I is a moment of inertia, it is a Planck's constant, and I is the moment of inertia, and it is given by mu r square, where mu is the reduced mass, that is equal to m1 m2 by m1 plus m2, and r is the internuclear distance. So this particular equation can be converted into the centimeter inverse unit. Then we have to divide it by an HC. So the equation will be equal to h by 8 pi square IC j into j plus 1 centimeter inverse. And this particular constant B is equal to j into j plus 1. Uh, h by 8 pi square I c centimeter inverse is known as the rotational constant B. So epsilon j, which is the rotational energy level, is given by B into j plus 1 centimeter inverse. Okay. So these are the allowed rotational energy levels for a rigid rotor molecule. Here we obtain the energy levels by substituting J is equal to 0, 1, 2, 3 values in this particular energy values. Here we can see the lower energy level, 0 energy level is 0. Then when J is equal to 1, we will get 2B. J is equal to 2, we will get 6B, then 12B, 20B, 30B, 42B, etc. Okay, and the selection rule for this transition is delta J is equal to plus or minus 1. That is, not all transitions are not allowed. Only those transitions when this particular selection rule is obeyed, that is delta J is equal to plus or minus 1, is only allowed from the rotational transition level. So when there is a transition from J to J plus 1, the energy required in wave momentum by unit is given by nu J plus 1 minus nu J is equal to 2B into J plus 1 centimeter inverse. Okay, so which can be, when we substitute the different values, we will get 2B centimeter inverse, and the transition between nu j is equal to 1 to nu j is equal to 0 is 2B centimeter inverse. From j is equal to 1 to j is equal to 2 is 4B centimeter inverse. J is equal to 2 to j is to 3 is 6B centimeter inverse. So following like this, the rotational spectrum will be given as this way. That is, 0 to 1 will be same as 2B, 1 to 2 will be seen at 4B, 3 to 4 will be given as 8B, 4 to 5 will be given as 6B, etc. etc. So we can see there is a, evidently these lines are equally spaced by an amount of 2B, which is known as the frequency separation. Okay, and the intensity of these rotational lines are given by the two factors, namely Boltzmann distribution law and degeneracy of a level. And this is the equation nj by n0 is equal to E minus delta E by kt. And we know delta Ej can be written as minus bhc by bhc into j plus 1 by kt. Okay, so the total population level can be written as nj by n0 is equal to 2j plus 1 e raised to minus bhc j into j plus 1 by kt. And this is the plot. Here we can see population rises to maximum as value increases, then decreases. The J max is obtained by root of kt by 2 bhc minus half.